Okay, everybody, I got 6:30. We're going to get underway. Um, Thanks for spending a little bit of time with me this evening. I don't know what about what it's like where you're at. Sun's come out, looks beautiful. So let's take care of school business, and maybe the weather will still be nice. And I don't know, I can cut some grass, something old manny like that. Uh, what we're going to do this evening, we're going to finish up chapter 10 at the beginning of class, and then get through about half of chapter 11, I think. I think we're on a really good pace this week to get through the ideas that we need to. Last time when we looked at chapter 10, we had calculations that were involved with this first grouping, involving the ideal gas law, including calculations involving partial pressure. We began to explain that a little bit by looking at kinetic molecular theory. And we have some new ideas that we're going to talk about here in just a moment that are in sections 10.8, 10.9. As I look at where we're at, where we're going, this is the same sort of figure that I had from the syllabus last time. So I see right now that we're going to be working, and I think we'll be in really good shape to probably wrap up all of chapter 11 this week. If not, just a little bit of a carryover to next week. But either way, we're in the home stretch, just 2 more weeks to go. And once again, the exam that we have within here, it's going to be a cumulative exam. So a lot of the ideas are things that we've already looked at, things that were from chapters 1 through 9. So as I think about where we're at, where we're going, I think our job for the next 2 weeks here, we need to be current and learn some new ideas and skills from chapters 11 and 12. But we also want to think about returning to the earlier content, because that's going to be the majority of the test. Okay. So what we find on a typical midterm, a given chapter might have 10 or 11 questions. On the final exam, it's probably about 5 questions, but it's going to be spread through over all of the content that we have. So as I think about this, this was the same kind of image that I grabbed from Mastering Chemistry as last time. So we know when the final exam is. Couple thoughts within here is I think what I can do to try to help you get ready. I think I can help direct you to the most relevant content from the different chapters along the way. And that's what I tried to do with some videos that I've posted within Perusal. I made those in the fall, and my intention then was the same as it is now. I really want you looking at the right material in the chapter. So I'm trying to give sample problems, direct you to what I think are the most important ideas and skills. And I think I can also provide feedback to you. So if you're reviewing ideas here the next 2 weeks, send me an email if you get stuck on something. Please bother me. You're at the top of my to-do list here as we try to wrap up this class. Now, if I was a student right here as I'm trying to bring this together, as a student, if I had a cumulative final exam that was about 2 weeks ago, I would give myself a deadline to try to master the ideas that we saw in chapters 1 through 6. Those were on our first and second midterms. I know personally, if I did not give myself a deadline, I would be working on those right up to the end. And I don't want to do that because I know we've got more ideas along the way. So those early ideas, if it's involving stoichiometry, if it's involving Hess's law, if it's involving assigning oxidation numbers, I know that those are so many of those are skills that you have. So one suggestion as a student, I would give myself a deadline. Maybe I would mentally say, you know, I'm going to have a test on chapters 1 through 6 next Sunday. I'd try to put some kind of deadline like that on my own schedule, because that would really allow me then to get that part taken care of, move on to ideas that we have in chapters 7 through 9, and try to stay current on this. I know a lot of times with a final exam, it can be that's cumulative. It can be a little intimidating. There's just a lot of content there. So one suggestion I have for you, try to take care of it in stages, okay? Try to take care of it. And if you can wrap up ideas that we had and skills from, let's say, chapters 1 through 6, you're in great shape to then move on to the stuff that we've had more recently. Now, what I'm trying to describe here, this is what cognitive science tells us, okay? There's a lot of folks within the class that are interested in either psychology, cognitive science, neuroscience. All that I'm describing is what I think you probably already know, that it's better to learn things in small increments and space out your learning. If you can cycle back and return to earlier ideas, that helps you recall the information and store it and remember it. If you can authentically test yourself and get feedback, that supports your metacognition, so you know what your strengths and weaknesses are. And my own theme, I really like to consolidate my understanding. I'd really like to make it so that by the end of this week, I've got a good summary for the first 6 chapters, and then I have another week to bring together the rest of the ideas. So I think we all probably know the best strategies, and I want to try to support you as you use them. Now, let me ask you this question. So I've mentioned as a student what I would probably try to do. This idea of I'd want to wrap up the ideas from chapters 1 through 6. Personally, I'd probably be setting a deadline for this weekend for me personally. I'm curious. Let me send you a poll on this. My question is, when do you think you'll wrap up most of your preparation for chapters 1 through 6? Would it be the end of this week, start of next week, end of next week sometime, maybe that final weekend? Or maybe you don't think about preparing for exams this way, which is fine. Maybe you've got a different strategy. I know a lot of times with a cumulative exam, it's as much psychological as anything else, meaning when do we allocate the time? What is our own behavior? When can we prepare so that we're not stressing about it? There's so much, I would say, sort of a mental game that goes along with this. Within this one, most of the folks seem to be saying your goal would be the start of next week. I think that's an outstanding plan. That would give you about 1 week then to move on to ideas that we had in the second half of the class. Ideas from 7 through 9, and then new ideas here from 10, 11, and 12. Try to give yourself your own mental schedule to stick with it. And if you can do both returning to earlier ideas and staying current, I think you're in great shape. And for both of those, send me emails. If you get stuck, I'd love to give you feedback and support on any of these parts. Okay. Now let's then revisit ideas that we had here when we're looking at gases. So we were looking at a description of the ideal gas equation, which includes relationships involving pressure, volume, and temperature, and the amount of gas that you have, moles of gas. So we've got our different values where we want to be able to do unit conversions. R was a gas constant. We had data here that at standard temperature and pressure, so that was 1 atm and at 273 Kelvin, 1 mole of an ideal gas has this volume of 22.41. Turns out that many experimental volumes, if you plug in the pressure and the temperature of STP for helium or for ammonia or for carbon dioxide, it comes out really close to this ideal value. And I think it should, because PV equals nRT, that's coming about from experimental measurements. They were done with gases like these. So they're trying to sort of say, well, what was the relationship that we saw? The relationship that we saw was this PV equals nRT given this particular gas constant. If these gases did not behave ideal, then you would not have come up with this generalizable pattern. So even though this is hypothetical, it works really well for a lot of these gases. If I look at something like helium, I would say is not just ideal, it's very ideal. It looks like it's spot on to what we would get if we plug things in with the values into PV equals nRT. Something like CO2, I would describe it as somewhat less ideal. We're going to contrast something being ideal and being real, a real gas. Now, it doesn't mean that real gases are in the majority. So many gases behave really close to this ideal value. But we're going to begin to look at what is a gas when it's behaving more real and less ideal. That's something we're going to talk about. Another idea we had was, what does it mean to have a mixture of gases? And how for many of the physical properties of gases, that would be like relationships as pressure, volume, and temperature. It doesn't matter whether the molecules are the same or different from each other. We could treat them independently. In PV equals nRT, the identity of that gas does not matter. So we could just treat the pressures independently if we were combining them. That was this idea up here of having the partial pressure being the pressure that one of the components is contributing. And we can just add up all of the partial pressures to get to the total pressure. We looked at a couple calculations involving that as well. The kinds of calculations that we went over that I described as typical ones would be simply using PV equals nRT where there was unit conversions, ones involving density, ones where we're using PV equals nRT and connecting it to reaction stoichiometry, and ones involving partial pressure. So within this group right here, I'm going to send you a polling question. Which of these, if any, involve information involving the mass? And I know this is a little bit, it might not be the best polling question. And the reason I say that is I think on these types of questions, you're going to be quite skilled to read it and use the information that's provided to answer the question. It might seem a little bit abstract when I say which calculations require mass information. Because when I'm writing this down and I'm thinking, well, here's an example involving stoichiometry. Here's an example involving density. I think I probably have something in my head that you could answer, you could solve, but I think in the abstract here, this might be a difficult question to answer. Within here, what I'm seeing is most folks are saying you definitely would require mass information of some kind when it's a density calculation. There's also some thought that you would use it for these other ones as well. I think mass information could be involved in these other ones, but it doesn't have to be. The only one where I really need to have some information about grams is when I have one involving density. Here was our example that we worked through last time, where we're calculating the molar mass of a gas given a particular mass and what it occupied, how we could calculate the number of moles using PV equals nRT. And we needed to now convert to get to molar mass by using that gram information. My thought within here is the only type of PV equals nRT calculation where we absolutely have to have a mass value is going to be one involving density. All of the other ones, we can look at the different relationships. We could get to moles, for example. We might not have to have mass involved at all, but for density, we definitely need to. We looked a little bit here then and began last time of connecting then this ideal gas equation, which would be experimental observations, to a description of it, an explanation using the kinetic molecular theory, or KM2. I brought up this idea that the ideal gas law, those are a set of observations. They're explained by describing the particles of gas according to the kinetic molecular theory, how a theory is explaining a law. And these were the components then of the kinetic molecular theory. These are a description of within the, if you want to say within the derivation, what were the gas particles like when they were bouncing into each other? What kind of paths were they taking? This was being used to then explain the relationship in PV equals nRT. So instead of stepping through those details once again, this PhET sim, this is consistent with an ideal gas. All of those descriptions within the kinetic molecular theory, that's what this visualization is showing, that sim is showing. To me, this is really helpful to try to remember their details. How the particles are moving in straight lines, how they're colliding with each other in the walls. When they're colliding with the walls, that's what gives rise to the pressure. How they're not losing energy in those collisions. How it's mainly empty space. All of these details, the designers for this PhET sim were very well acquainted with kinetic molecular theory, and that's what they're describing within it. So I find this is a useful way to remember what it was like, what it's like. So one feature that we saw and we explored was, well, what happens if you have the same gas, but you change the temperature? Changing the temperature is increasing the kinetic energy of those particles. It's increasing their velocity. It's showing that you change the distribution of speeds by increasing the temperature. So that's one relationship that we explored. Another one we explored was, well, what happens in terms of the mass? What happens if we're thinking about heavy particles that are in motion, and at the same temperature, we add in some lighter particles? This is where we were finishing last time. If they're the same kinetic energy, same temperature, 1/2 mv squared is true for both of them. It would equal the same value. But if something has a smaller mass, it had to be moving with a higher velocity. So it led us to this description here. Well, what if we have different gases, but they're at the same temperature? So the variable now is the mass of the gas. The lighter particles, well, they must have a higher average velocity in order to have the same kinetic energy. So you see this distribution here, how the lighter molecules like H2 or helium are moving at a much higher speed than the larger ones like O2 or N2, really dramatically so. Now, this idea that lighter particles must have a higher average velocity, that's going to lead me to suggest, there might be another property of a gas besides its density that also depends on the mass. This particle motion might give rise to another property that we could measure as well. And that's what we're going to get here in 10.8. So here's the phenomena to be familiar with. So I grabbed a picture here of some roasted coffee. Okay, I make coffee every day. That's one of my jobs around here. Okay, it seems like during pandemic time with my wife and I working at home, we have different jobs. Mine, I make the coffee. So I definitely notice each time I open up the bag of it, I mean, you really get the aroma. It's really pronounced. So my picture, what I'm trying to show right here is, let's say on this left side of the container, that's where the coffee particles were, the gaseous coffee particles. If you remove the barrier that sent those particles, they just move and they fill up the entire container. Removing a barrier and having the thing go from a higher concentration to something that's in a lower concentration and fill up the space, that's called diffusion. I want to contrast that with this phenomena. What if instead of removing the entire barrier, and instead of removing and opening up the entire bag, what if you just put a really small hole into it? Just a really small pinprick. Over time, the gas particles would find their way through that hole as well. But you're not removing the entire barrier at once. This is called effusion. The phenomenon that we're interested here is going to be this effusion. What does it mean to just have a very small opening and allow the gas particles to find their way through that? So, question for you. Let's say you had two different types of gases in the container, and you have that small hole there. Which one do you think would be leaving at a faster rate? Which of the ones that would be leaving the container at a faster rate and going through the partition? Would it be something that was a heavier gas or something that was a lighter gas? Let me send you this one as a polling question. Do you think the heavier gas would go faster, higher rate? The lighter gas? Would all gases have the same rate? Or maybe there's another variable that we need to consider. Take about 5 more seconds. Okay, strong vote here favoring the lighter gas. Let's look at it sort of at the particle level for what's taking place. So let's put both light and heavy particles within this chamber at the same time. First, the heavier particles, then the lighter ones. Lighter ones are moving with a much higher velocity. They're bouncing around much more frequently. The lighter particles are striking the walls of the container, it appears, more frequently too. So we put a little hole there at the top. In order to go through the hole, the particle needs to strike that part of the container. I see the lighter particles striking all parts of the container more frequently. They have a better chance of leaving. I saw a heavy one leave there just a moment ago, but overall, the lighter ones, they're striking the walls more frequently. In order to leave, you got to strike where the hole is. And it sure seems like the lighter ones that's happening more frequently. So I'm going to agree with you, absolutely. The lighter ones, they had a faster rate of effusion. In fact, the calculation for it I show here at the bottom. The rate of effusion for one gas relative to another one is equal to the square root of their masses, their molar masses, but notice how the masses now are flipped over. So this is another way of saying if something has a smaller mass, it will have a faster rate. This is one that I think we want to know both conceptually and be able to do the math. So our setup, once again, the rate of effusion that something would be leaving through the pinhole of gas number 1 over gas number 2 would be equal to the square root of their molar masses, but the molar masses are flipped over. That's another way of saying the lighter particles would leave more quickly. This would be an equation to do calculations with. We also look at it conceptually. Now, this is what's being used to explain a phenomenon like this. This is something you might have observed, okay? You could have a nitrogen balloon and a helium balloon. You come back the next day, the helium balloon, or a couple days later, the helium balloon seems deflated. Whereas the nitrogen balloon or an air balloon, it doesn't change hardly at all. This is exactly related to Graham's law. Much lighter mass for the helium, finding the opening more, deflates it. Now, as I pick this picture here of a child with their deflated balloon, I think you could now provide an extremely strong explanation for a phenomenon like this. If you've got a child in the family, you've got a little sister, who knows, and they said, look, I had this birthday balloon, now it's deflated. I wonder what's going on. You are empowered now to give an extremely good answer. You can talk about the kinetic theory, molecular theory. You can talk about the molar masses of the gases. You can, I mean, all I'm saying is use that information wisely. We are at the stage of the course in chapters 10, 11, and 12, where we're going to bring together a lot of ideas that now can explain everyday phenomena. Things like, I wonder why my helium balloon deflated. Use that power for good, not for evil, okay? You are going to be in a great position to be able to explain these. And I say that as someone who knows general chemistry and has many occasions with friends and family to share that information, and it is not always welcomed. So use that information wisely. Word of caution there. Now, this would be a question here. This is a end of chapter 1 on this. I'll give you a second. Read that one over for me. As you look at this, one question I'm seeing within the chat here, as far as when you have a balloon where the pores are, in your standard rubber balloon within that, you have pores throughout that it can go, it can find openings throughout, okay? There's, for something like helium, it can make its way through the actual body of the balloon. That's why you see now they do more where they'll sell them with like latex balloons, or they'll sell balloons where it has like a coating on it. The idea there is that removes then the standard, the holes that you have, so it stays inflated longer. This one with right here, this is back to being more in the chemistry domain as they're talking about naturally occurring isotopes. As I look at this, there's only one variable I need to consider, and that's the mass. I'm thinking that if the particles have a smaller mass, Those gas particles have a higher velocity. They're striking the walls of the container more frequently, and that would lead to a higher rate of diffusion. This is one I grabbed as an end of chapter 1. This brings together conceptually so much of chapter 10. Within chapter 10, that whole first part, ideal gas equation, we went over like 4 or 5 different kinds of calculations. I would expect you'd have probably 3 of those different types on your final exam. You might have a gas one involving partial pressure, one involving stoichiometry, one involving density. That's what I mean with like 3 or 4 different types. Those would be really representative ones that I would expect on the exam. When it comes to questions on this, what we're talking about tonight, I think something involving rates of diffusion would be a very leading topic. And then the questions involving the kinetic molecular theory, a lot of times they're ones like this. I mean, you're not going to write an essay on the kinetic molecular theory. So they're looking at different conceptual applications. And this end of chapter 1, I think, is right on that learning objective. So it says, consider the samples of gases shown in this image. If the 3 samples are all at the same temperature, rank them with respect to these different variables. Now, within your ranking, I know some values might be equal within the ranking. It's sort of like in mastering chemistry. If your values are the same, overlap them, okay? So take a second within here. See if you can rank these in terms of the total pressure. We're going to step through each of these. Take a second, look at each of these, case 1, 2, and 3. Try to put them in order based on the total pressure. Here'd be my thought on this one. I think scenarios 1 and 3 in my image right here, I think they're trying to show that they have the same total pressure. If they're the same temperature and they're being shown here, let's say in the same size container, I'm going to add up the total number of particles. And I see the same number of particles in case 1 and in case 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And you might say, yeah, but one of these is nitrogen. It's got more nitrogen there. Should that matter? Doesn't matter. If we're looking at the total pressure, it's only involving the total number of particles. So I think 1 and 3 both have the greatest amount, and number 2 would be the smallest. Take a second now. How about the partial pressure? The partial pressure for the helium. You see what the symbol is for helium there. Try to rank the partial pressure for helium across those 3 now. When it comes to the partial pressure of helium, we can treat the helium independently in each of those. We can just look at the helium particles. In case 1, this would have the greatest partial pressure of helium because it's got the most particles of helium. Second most, and then the least. So with the partial pressure, I'm just looking at that particular component. Next one I'm going to send to you as a polling question. What would be your ranking here for the density? And I'm going to make it multiple choice. Try to put these in order from the box, the container there that has the largest density to the smallest. And if you finish that one, also try to think about prompt D in terms of thinking about a ranking for the average kinetic energy. For the density, we're seeing a really strong consensus that 3 is greater than 1, which is greater than 2. I agree completely with that. I've got equal number of particles in 1 and 3, but nitrogen, they have a larger mass than helium. So I absolutely agree that 3 is greater than 1, which is greater than 2. As far as the average kinetic energy, well, that's what the temperature is measuring. If they're all at the same temperature, they all have the same average kinetic energy. Quick thought in terms of this format right here, this sets up great for a multiple choice test because you can just grab, and these are so easy to make the images, and you've got all of these different variables that you can look at, okay? So as far as a question from chapter 10 from the second half, involving the kinetic molecular theory, something like this, I think, is really representative. One more thought within here. So as we begin to think about ideal gases and now expanding that to be real gases. In a gas right here, this is something that I discussed a little bit within the pre-class video where we were comparing aspects of the kinetic energy and the attractions between the particles. For an ideal gas, we would say that the kinetic energy is greater than any of the attractions that were there. And in fact, for an ideal gas, there were no attractions. The particles only travel in straight lines. They're not like there's an attraction like you might imagine between two magnets where they start to pull or edge towards each other. For an ideal gas, they're just all moving in straight lines. With a real gas, we're going to begin to question some aspects of that model. We're going to add some more complexity to say, well, what if there are actual attractions there? That's going to turn PV equals nRT into a more complex relationship, a more complex equation. This is something where you're not going to do any math with, but I want you to understand it conceptually. Within this one right here, there are two different variables. This is just PV equals nRT with two more variables added. I see a term A and a term B. Everything else in here is still PV equals nRT. A given gas, a given substance has its own A and B values, its own characteristics. Instead of saying every gas is a gas is a gas and the only variable that might be important is its mass, they're now starting to add characteristics of the gases here, these A and B values. These are used to describe a gas when it begins to have real behavior. The two different variables, A corresponds to attractions that might be present, and B corresponds to the size. I've seen exam questions when they begin to discuss these real gases in what's called the van der Waals equation. One thing that I've seen before is, well, tell me about what the constants are. A corresponds to the attractions and B corresponds to the size. The role of the attractions there, they make it so that the volume of the gas ends up being smaller than you might have predicted. The pressure would be less. That's another way of thinking about it. If there are attractions between these gas particles, instead of simply striking the wall with their full force, they might be somewhat attracted back to their neighbors that are inside the container. This reduces the pressure that they would have just striking the walls. So that's what the factor that the A does. Due to attractions, it ends up minimizing the pressure that you end up observing. And the size is just the opposite. The size is like a repulsion. This makes the apparent volume larger. The pressure seems to be greater. My point with both of these is if we have one thing making the pressure seem somewhat smaller and the other make it seem somewhat larger, those are competing forces. It's going to depend on other conditions to see which one wins. How does the real gas actually behave? We're not going to do calculations with that, but I think that this is a useful way to begin to now take gases as they behave in a real manner and connect that with chapter 11. Now, to begin to understand here these van der Waals constants, it's a little tough to make sense of them in this table right here. I took these and I made an Excel plot. okay? I put a plot where the x-axes are the different A values, and the vertical axes here are the different B values. I just took the ones right from this table and made a plot right here. So first of all, help me read the plot here. The x-axis refers to the attractions, and the vertical axis refers to the size. Let me send you a polling question on this one. Does it seem like there's a relationship between the attractions and the sizes? Based on this figure, are stronger attractions found between what types of gas molecules? Larger ones or smaller ones? As I look at that plot, it looks like a pretty good fit. It looks like if I were to add a line to that, it would go through almost all the data. I think I've got a pretty good correlation between the volume and the attraction. And folks are saying that the stronger attractions correspond to the larger gas molecules. Strong consensus on that? I agree with that. If I were to add a fit right here, as the size got bigger, the attractions got bigger. That goes through almost all of the points that I see right here. There's one outlier here though. H2O seems a little bit different. H2O, as I look at it, I would have thought based on the pattern, it should be right now over here on the left-hand side. It shouldn't have that much of attractions between different H2O molecules. It's not very big. And yet it's got a much greater attraction than it should for its size. So take a second, look over here amongst these different gases. See if you can think about what makes H2O different from all of the other ones. As I think about some of the chemistry we've been talking about, H2O, that's the only polar molecule I see listed there. I've got these diatomic ones that are not polar at all, N2O2, Cl2. The more complex ones like CH4, well, that's a tetrahedral. I know according to my VSEPR predicted geometry, when I look at the molecular polarity, it's nonpolar. CO2, okay, that's linear, that's also nonpolar. CCl4, that's also a tetrahedral, that's nonpolar. The only one that I see within here on this provided list is H2O. So a couple generalizations right here. It seems like polar molecules, they might have greater attractions with each other things being equal, than nonpolar ones. And another general one is that the stronger attractions for these gases are found between the larger molecules. Those are two takeaways that I would say when I'm beginning to look at the characteristics of real gases and think about how they're different than ideal ones. A larger size and mass, this seems to be leading to larger attractions and greater attractions, intermolecular forces being the attractions between those gas molecules. And with polar molecules, those are also leading to greater intermolecular forces. I'm trying to bring up the idea of intermolecular forces because that's exactly where we're going next in chapter 11. Before we do, let me give you a couple of suggestions here at the end of chapter 10 for some suggested problems. So this one at the top right here is asking qualitatively, okay, here's a particular scenario. Tell me about different things and how you might be able to change different variables. So this I would put it into the conceptual category. One thing I want to draw your attention here, if it says root mean square speed, that's just a technical term. It's just the velocity. It's just the speed that we're looking at. Don't let this root mean square part freak you out or anything. They're just talking about changing the velocity of the molecules there. This whole set right here, these are all from things that we've explored a little bit this evening. These are all sort of the conceptual ones. This very last one, this is sort of how I've seen the question shown on the exam before, where it's asking about the van der Waals equation. That's the one describing real gases. It's a question saying, well, tell me about these constants A and B. That's what I've seen sort of the format for what might show up multiple choice on a test. Let's dive right here then into chapter 11. So within chapter 11, we're going to look much more closely at these intermolecular forces and begin to think how they lead to different properties that we'll be able to explain involving liquids. So when I'm thinking about here intermolecular, I'm thinking about the attractions that take place between molecules. We can think about that for what's taking place in gases, liquids, and solids. And then we can focus then on these intermolecular forces. Now, when this molecular part, we've definitely looked at things that take place within the molecule. When we looked at covalent bonds, polar covalent bonds, the bonding in H2, the bonding in O2, the bonding in CO2, those are all within the molecule. In all of those cases, we saw how if we had opposite charges, there would be an attraction. If the electrons could be found between the two nuclei, that could lead to a net attraction, and it could hold the atoms together, it could form a bond. So if we start to think about what would lead to bonding, or excuse me, attractions between the molecules themselves, not within the molecule, but between different molecules, it's got to be due to the charges once again. As a chemist, that's what holds things together. Opposite charges attract. So what we're going to do is we're going to look at these different descriptions for how we can have opposite charges attracting. And we're going to be using those to look at different types of intermolecular attractions that are holding these different molecules together. That's what our goal here is within chapter 11. So we've been looking a lot at different molecular and ionic compounds this whole semester. With ionic compounds, what comes to mind, something like NaCl, where I've got these positive, negative throughout, holding the whole thing together. In chapter 8, we looked at different details. We looked at the energetics to get to those with the Born-Haber cycle. We looked at the lattice energy. We did rankings involving lattice energy. Those are the things that we did when we saw how these ionic compounds had a whole bunch of cations and anions stuck together. Here's an image for CO2 on the right-hand side. So this is CO2 as a solid. So if I look at this and try to connect it to what we've been talking about, I see that there is this specific discrete CO2 molecule. And in fact, I see many of those that seem to have some kind of pattern. We'll look at patterns like that when we look at solids in chapter 12. This is a molecular solid. I have these different molecules that are all stacked together. CO2, well, that would be the molecular formula. That's not an empirical formula. That's telling me the distinct building block that I have. And that's why we name it, recall back in chapter 2, as carbon dioxide. That dioxide had to tell us how many oxides that we had there present, how many oxygens we had present. We've learned a lot about molecules like this. We've learned about the bonding within the molecule. And we also learned how, based on the shape of it, even if you have bond dipoles pointing towards the more electronegative atoms here, they end up canceling out, because as a vector quantity, we had equal pulls and pushes in each direction, making CO2 nonpolar. And yet it sticks together. It sticks together as a solid. Dry ice, that's what solid CO2 is. So even something here that is a molecule that is nonpolar, we still need to come up with an explanation for how it can stick together as a solid, and we will here. In the pre-class video, we looked at some demonstrations involving CO2, Br2, and I2. When I asked folks about, well, can you describe the bonding within each of these? I thought people did a really good job, whether we were looking at valence bond theory or molecular orbital theory. I thought that that's something that we've been working on recently, and I was impressed with how people are bringing those ideas together. People were also able to think about whether this was a polar molecule or nonpolar one. That last question right there, is the molecule a polar molecule or a nonpolar one? That's going to be a really important skill that we need in chapter 11. So that tells me our VSEPR predicted geometries, something that we did at the start of chapter 9, that's going to be a really important skill. Now remember, within our VSEPR predicted geometries, there were multiple things right there too. We had to start with the Lewis structure. We had to consider the electron domain geometry, the molecular geometry, and then considering whether the bond dipoles would cancel. All of those, I think those are skills that you're getting better and better at. We're going to use those here in chapter 11. If I'm thinking about CO2, I'm thinking about a diatomic molecule. And whether I'm thinking about Br2 or I2, in each of those cases, I'm thinking about diatomic molecules. All of them are nonpolar. If I add information about the intermolecular forces, I think they're greatest here in the solid and smallest here in the gas. I am in fact thinking that it is the strength of those intermolecular forces that is determining whether this is a solid, liquid, gas at a particular temperature. At room temperature, we have one that would be a gas, one that would be a liquid, one that would be a solid. Now, how can we begin to understand this? First of all of these molecules, CO2, Br2, I2, I think they're all pretty similar. They're all nonpolar. There are differences in size. Iodine's larger than bromine, which is larger than chlorine. We've also seen that there were stronger attractions. Just a moment ago, the data said that when the molecules are larger, it leads to stronger attractions. Okay, that's consistent with what we have right here. We have stronger attractions for a given temperature, which is making I2 a solid and CO2 a gas. So this is consistent with what we saw just a moment ago when we were looking at real gases as well. So let's explore this idea a little bit more. When I'm thinking about a gas, I'm thinking that the particles are far apart, they can move around with complete freedom. When they're a liquid, the motion is restricted a little bit, and when they're a solid, it's restricted even more. The kinetic energy, though, can be the same in all of these cases. At room temperature, they all have the same kinetic energy. Don't mistake the kinetic energy for the freedom of motion. Kinetic energy, that's the energy that we have associated with the motion, 1/2 mv squared. There is still motion in the solid. The particles are still vibrating around. They don't have to be completely separate from each other in order to move. All matter is still moving like that. And in fact, room temperature right now, the matter in the room, the atoms around you as they're jiggling, even within a solid, it's not stopping a bit. So if you were to look around the room right now that you're in, I'm sure you see a lot of solids. You probably see some wood, you probably see, I don't know, some aluminum, you might see a pencil. You've got a whole bunch of solids in the world around you. We live, in a world of solids. You might have a couple liquids. Maybe there's some water in a glass. Maybe there's some Coca-Cola. I don't know. There's probably a liquid here or there. And there's definitely gases in the room, even if you can't see it. Now, within that whole group right there, all of those substances right now in your room, they all have the same average kinetic energy because they're all at the same temperature. They're all at room temperature. Those solids in that room and the gases in the room, they all have the same average kinetic energy. But for some of them, for that amount of kinetic energy, they're not held together very well. They're gas particles that are just moving around. And other ones are quite rigid, okay? If you've got your table right there, if you knock on it right now for that same amount of kinetic energy, it sure seems a lot more stable and stuck together because there's greater attraction between those particles. So I don't want us to confuse something being solid, liquid, and gas in the kinetic energy. The kinetic energy, that has to do with the temperature. And right now in your room, all of those substances have the same average kinetic energy. What makes them different right now, what makes one of them a liquid and one a solid and one a gas, it's the strength of the intermolecular attractions that they have. With a gas, the kinetic energy, the energy that they get just from the temperature within the room, is a lot greater than any attractions that would be holding them together. For a liquid, it turns out they're about the same, And for a solid, that amount of energy associated with the temperature, the kinetic energy, is a lot less than any of the attractions. So they're all stuck together still as a solid. In an interesting way, that's a powerful part of, I think, of our explanations. We see very different properties as far as things being solid, liquids, or gases, but it comes back to comparisons with the kinetic energy they have, their temperature dependence. If I'm thinking of something like Cl2, I show here how it's a liquid in a particular span. If it's at a lower temperature, it can be a solid, a higher temperature, it's a gas. My point is you can change CO2 from a solid liquid to a gas by changing the temperature. Same thing with Br2, turns out it's in a different range, or I2, it's in a different range. My takeaway within here, I'm beginning to connect different properties of the substances with the intermolecular forces present. Two of them right now I want us to be aware of: the boiling point and the melting point. The higher the boiling point, the stronger the intermolecular forces. The higher the melting point, the higher and stronger the intermolecular forces. Easy to remember, right? Because they're all, the bigger the number means a bigger number. A stronger intermolecular force is going to lead to a higher boiling point and a higher melting point. That right here with our initial one, our comparison of solids, liquids, and gases, let's have that be our main takeaway. That our main thing that we want to understand there is melting point and boiling point. Those are useful ways of thinking about something being either a solid, liquid, or a gas. And both of those have larger values when there are higher, stronger intermolecular forces. Next task for us is let's look more closely at what's giving rise to different intermolecular forces. Then what we're going to do next time is we're going to expand and look at more properties. But in order to do that, let's try to get a good understanding on what really are intermolecular forces. Now, they're named different ways. Let's explore each of those. If we think about this picture, I go back to the ones we saw just a moment ago. I mentioned how water, H2O, is a polar molecule, somehow gave us greater attractions. I think we might have a head start on understanding that. We've looked at H2O quite a bit. We know that we have a region that's partially negative and regions that are partially positive. So it has a dipole moment. I'm definitely seeing positives and negatives there. We'll come to that, but let's start with these ones that are nonpolar. For those nonpolar ones, a larger size was associated with greater attractions. I saw some really good questions in perusal on that. Let's understand what's going on there. So first of all, I'm going to name these as London dispersion forces, or sometimes you might see just the dispersion forces. This is the phenomenon that's present. This is the kind of attractions that hold together helium atoms. Helium, you've got to get it really cold in order to have helium atoms go from a gas to a liquid. How cold? You've got to stop almost any motion whatsoever. You got to go down to about 4 degrees Kelvin. It's almost as low as you can go. But if you get down to about 4 degrees Kelvin, I think it's 4.2, you can have helium stick together and be a liquid. You can make liquid helium at about 4.2 Kelvin. So this tells me that helium atoms, even though they're almost always a gas, if you reduce the motion enough, if you have the kinetic energy get down small enough, they can stick together and begin to form a liquid. What causes them to stick together is the first force that we're talking about, dispersion forces. Here's the phenomena. So let's say we bring together here at the top of the image 2 different helium atoms. The black dots are the nuclei. They each have 2 electrons moving around somewhere. If we look with the images in the center right there, what they're trying to show is the one on the right-hand side, it just happens to have both of the electrons on the same side of the atom. Is that crazy? It's not crazy. The 2 electrons, they're in a 1s orbital. They're moving around within that. They're found based on their probability anywhere within that orbital. Is it unusual to have both of them on the same side? That's not crazy. I'm sure it happens all the time. But what that does is it makes the left-hand side of that atom somewhat negative, and it makes the right-hand side somewhat positive. So that's what they're trying to show down below. It just happens that you have a dipole there. You've got a positive and a negative region. You have this side partially negative, partially positive. That's being described as an instantaneous dipole on this atom B. It wasn't there ahead of time. It just happened based on the motion of the electrons. But now if you've got another neighboring atom nearby, it can respond to that. It can have a shifting of the positive towards the negative. And notice how they're trying to show that at the bottom right there. We have in one case where it just happened that we had a partially negative and partially positive. And for a neighboring atom right there, it can respond to that. They're trying to show now that we have opposites attracting, positive and negative. We have a reason for those two to begin to stick together. These dispersion forces, these are present in any molecules that we have, because all that it took was just chance. It just took chance that one side was negative and one side was positive, and it could then influence a neighboring one. When I'm thinking about London dispersion forces, if I have a larger molecule that has more electrons, it's more what's called polarizable. It's easier to shift the electrons from one side to the other. They're not as held as tightly. This can lead to stronger attractions. This is an important finding for us. This explains all of that data that we had earlier, where we saw nonpolar molecules that had stronger attractions as they got larger. They had stronger attractions as they got larger because what was present were these London dispersion forces. As they got larger, they had a larger electron cloud that could be shifted around and lead to this attraction that was between two of them. This is why things, if they were larger, were leading to stronger intermolecular forces. This is what's explaining our group here that we have. As I go from Cl2 to Br2 to I2, we're getting larger and larger. We're getting stronger and stronger intermolecular attractions. We're getting stronger and stronger dispersion forces. Let's look at some more data. So here we have different ones involving boiling point. F2, Cr2, Br2, I2, as we go right down that column, they're getting larger and larger molecules. Boiling point's going up. Intermolecular forces are going up. What if instead we look at the noble gases, column right next to it? Neon, argon, krypton, xenon, we're going right down that column. In that case, boiling point's going up as well. London dispersion forces, okay, now we're going to have a resource that's helpful for us. With London dispersion forces, we now have a tool to begin to make predictions involving things like boiling point for these nonpolar molecules. It's empowering us to be able to not just say, oh yeah, these have different values. We can explain them. When we're thinking about these London dispersion forces, I'm thinking that a larger molecule, when there's more electrons, is more polarizable, meaning it's more easily becoming polar, and that's leading to stronger attractions. Now, when I'm thinking about how this shows up on tests, I've seen two different formats. If you tell me the boiling point of something, you're really telling me about the strength of the intermolecular forces. Something with a higher boiling point has stronger intermolecular forces. Sometimes you're going to be asked to make predictions, and sometimes, given some data, you're going to be asked to provide explanations. Let's look at this example right here. Which of these would you say has stronger intermolecular forces? In order to answer that one, this would be a case where, look at the data. What has the stronger intermolecular force? The N-pentane or the neopentane? I'm putting this in the category of, If you give me information about the boiling point, you are telling me about the intermolecular forces. So if I look at both of these, N-pentane has a boiling point of 309, neopentane at about 283. So right away there, I'm going to stop the poll because you're agreeing with the same thing I would agree with. You're saying that, you know, the one with the higher boiling point, okay, that's the one that has stronger intermolecular forces. I completely agree. Now, the reason I'm bringing up these as an example, both of these have exactly the same formula, C5H12. The only thing that's different is how those atoms are arranged within the molecule. This arrangement here is leading to stronger intermolecular forces, stronger dispersion forces. What's going on between the two of these? This one at the top, they're in chains that can get close together. This one at the bottom, they're in spheres and they don't have as much surface area for how they can contact each other. This is a factor that makes London dispersion forces can heighten them. If you have these long linear molecules that can fit together like one piece of bread with another one, you've got more surface area between the two of them. So you can have, therefore, greater attractions take place versus things that are spherical where there's just one point of contact between the two of them. So for each of these, as we try to look at their features, with dispersion forces, I try to help you understand, well, where are they coming from? I try to help you understand, well, when would they be present? That's easy. You always have dispersion forces. What factors make them larger or smaller? London dispersion forces are greater, they're larger when you have larger molecules with more electrons that are more polarizable. You can shift the electrons more, and that leads to stronger attractions. And then we added another detail. If you have very similar in size, but you have these longer linear molecules, that makes dispersion forces even greater. That's our overview of dispersion forces. Here, let's look at some data. So here I show 4 different molecules. For each of them, we have the molecular weight, that's what MW is, a dipole moment, that's what mu is, and the boiling point. So take a second, first of all, look at the boiling point data. Which of these has the weakest intermolecular forces? Which has the strongest? See if you can rank them in terms of intermolecular forces. Now, there's a lot of data provided there for each one. There's a name, there's a formula, there's molecular weight, but it's easy to put them in order in terms of intermolecular forces. I'm just looking at the boiling point there. And in fact, they're already in order based on the smallest boiling point to the largest. Now, if I were to say, does the London dispersion force, does that explain this ranking? In order to do that, I'm going to look at the molecular weights. Because I just said a moment ago, something with a smaller molecular weight would have weaker London dispersion forces. Something with a larger molecular weight, more polarizable, it would have larger London dispersion forces. That might be modified a little bit based on their geometry. As I look within this one, okay, molecular weight of 44, 46, 44, 41, they all seem really similar to each other. And in fact, the one with the smallest molecular weight had the strongest intermolecular forces. So do London dispersion forces do a good job of explaining this? It doesn't look like they do a good job at all. My point is, we have different types of intermolecular forces. Our first one were dispersion forces. They don't do a good job of explaining what's going on here. We need to think about another type of intermolecular force. If I look at these, what explains the difference, look at their dipole moments. That's what this mu value is. This is showing whether they're largely nonpolar or polar. This one here on the left, propane, it's really a nonpolar molecule, a really small dipole moment. The one on the far right, acetonitrile, okay, that's a polar molecule, a much larger dipole moment. This is the second type of intermolecular force we need to know about. It's called dipole-dipole interactions. Our first one, London dispersion forces, we just happen to have a dipole instantaneously. In this case, we're saying, what if you have a clear dipole there? You got a clear partial positive and a clear partial negative. Those will now allow them to stick together. Dipole-dipole forces, these require polar molecules. If you have a dipole moment, that's telling you there's a polar molecule. So our first one, London dispersion forces, you didn't need polar molecules. They were always present. Our second one that we're interested in, dipole-dipole forces, these are present when you have polar molecules. Let's look at our third type. So we've mentioned dispersion forces, dipole-dipole, which involve polar molecules. Third one I want to bring up is called hydrogen bonding. So first of all, let's consider these simple molecules we've seen many times. H2O, HF, and NH3. Take a second, let's think back to things that we did in chapter, when was it? 8, 9, I'm losing track here. Think about the bond polarity in each of these, and then think about whether the molecules are polar or not. Two different questions. Bond polarity, we're thinking about differences in electronegativity for a specific bond. Whether the entire molecule has a dipole moment or not, that requires consideration of the VSEPR predicted geometry. Take a second, see if you can think about both of those, and then I'll share my answer. When I'm thinking about bond polarity, I'm thinking, okay, fluorine is the most electronegative. The atoms immediately to the left, nitrogen and oxygen, also quite electronegative, but I know it gets more and more electronegative as I head towards fluorine. And I'm also thinking, well, where's hydrogen found within this? Just to the left of carbon. So I think in terms of the bond itself, hydrogen bound with fluorine, that bond right there, that's more polar than if it was with oxygen than it was with nitrogen. So in terms of this one, in terms of ranking the bonds and their polarity, I think these are all polar bonds for sure. And I think the most polar was with HF. In terms of the molecules themselves, I think all of these are polar molecules. I think all of these are ones that we've seen before, and we'd recognize them all as being polar molecules. Now, let me begin to think about these ideas and where hydrogen bonding fits in. All of these are going to have dispersion forces, because dispersion forces are always present. All of these are going to have dipole-dipole forces because they're all polar molecules. What I'm trying to do right here is the skill of, we want to be able to look at the formula for something, think about what that molecule is, and classify which intermolecular forces are present. So for these right here, I'm thinking dispersion forces are present for all three. And because they're all polar molecules, dipole-dipole forces are present as well. I'm still getting to the one called hydrogen bonding. So here we show H2O, HF, and NH3. There's a polar bond within each of those, a polar covalent bond within each of those. If I were to look at the electron density right here, I've got a region in each case that's negative and partially positive. In each case right here, oxygen is very electronegative, fluorine is very electronegative, nitrogen is very electronegative. These are all making polar molecules. Within these molecules, I see hydrogen is bonded to a very electronegative atom. The hydrogen bond that we're talking about here is an intermolecular force. It's not within the molecule, it acts between molecules. It's between one molecule and another molecule. So the first thing I want to get clear on, when we call something a hydrogen bond, the name sometimes doesn't help us because students mistake and they think, oh, well, that's the bond that is within the molecule. Hydrogen bonding is like other intermolecular forces. It's an intermolecular force. It's between molecules. The condition for this to take place, though, we have to think about, well, what is taking place within the molecules themselves? In order to form this intermolecular attraction, I need to look in the molecule and see that I have hydrogen bonded to either nitrogen, oxygen, or fluorine. That is a requirement to have hydrogen bonding take place. In order to have hydrogen bonding take place, I need hydrogen bonded to nitrogen, oxygen, or fluorine, these very, very electronegative atoms. This is the representation for how it shows up. It's showing up as a dashed line here. Notice how the authors did it. They first had molecules by themselves. The hydrogen bond, which is intermolecular, is this dashed line that shows up between them. In each of these cases, you've taken something that has a partially negative charge on the oxygen, nitrogen, or fluorine, and on the neighbor, you have a hydrogen atom that's partially positive. And that's leading to the attraction between the two of them. The attraction between the molecules, it's being shown as a dashed line. That's what hydrogen bonding is. Let's see if you can sort of visualize this. So in this, I show a combination of H2 molecules and H2O molecules. If you were to look at this, where would hydrogen bonding be taking place? Let me give you some choices. I tried to list all the different options here as choices. Would it be scenario 1, 2, 3, 4, 5? I tried to list all the different kinds of spatial features that I could see right here. And if we're talking about hydrogen bonding now as an intermolecular force, I'm curious within here. Which of these do you think are examples of hydrogen bonding? Let me send you a poll on it. We've got 1, 2, 3, 4, 5 different options. Which of these do you think illustrates the phenomena of hydrogen bonding as an intermolecular force? And I was a little hard on myself earlier when I was asking that question. And I said, yeah, this might not be a good polling question. You know, maybe you don't visualize what I visualize, etc. But the one that I'm sharing right now, I think this is a really good polling question. This is giving me really good insights into how you're seeing this. And it's giving me an opportunity to clean some things up. So here's what the consensus is. So the consensus right here, there's some votes for 1, 2, and 4. And the strongest votes for where hydrogen bonding would be taking place is between 3 and 5. Examples 3 and 5. So let's look at those within the set. So first of all, I'm going to quickly say 1 and 2. I am not going to call those hydrogen bonding because both of those examples, they are taking place within the molecule. Hydrogen bonding is an intermolecular attraction between molecules. So right away, I'm not looking for bonds within the molecule. This looks like a sigma bond between two hydrogen atoms. This looks like a sigma bond between hydrogen and oxygen. Those are not what we're calling hydrogen bonding because they are not between the molecules as an intermolecular force. So I'm gonna rule out 1 and 2. If I'm looking at number 4, there were a small number of folks that voted for that one. I'm also going to rule out number 4. Within 4, I'm trying to show some kind of relationship between the hydrogen that was in H2 and the hydrogen that was in H2O. That's not going to give rise to hydrogen bonding. Remember our description for what we needed for hydrogen bonding. We were looking at a molecule like H2O in which the oxygen was partially negative and the hydrogen was partially positive. This could then lead to hydrogen bonding where that hydrogen atom could be attracted to a neighboring molecule that was partially negative. So if I look at here examples 3 and 5, look carefully at those between 3 and 5. Are they both hydrogen bonding or not? I think only one of them is. I definitely like choice 3. I think within this here, this oxygen became partially negative, and each of the hydrogens partially positive. And the neighboring one, this oxygen became partially negative, and these hydrogens became partially positive. That's great. Now I have an attraction between the hydrogen, which is partially positive, and the oxygen partially negative. That right there, number 3, absolutely classic example of a hydrogen bond. Over here for number 5, look closely at it. This is like a where's water or something. Where's the hydrogen bonding? I don't think this is hydrogen bonding. I like what's going on with the H2O. I've got the oxygen, which is partially negative. But if we look at the neighboring ones, what is that being shown with? That's being shown with an H2 molecule. These hydrogens here, they're not partially positive. It's not saying here's an oxygen with any hydrogen. It needed to have the condition like we see over here at number 3. I think number 3, that's our only example of hydrogen bonding. I think over here at number 5, it's not. This idea of can we look at the image and try to match it? That's something we can practice next time too. Okay. I think if we practice it another round, I think we'll be in really great shape with that. When we're looking at, and we'll see how far we get within this last one. Within this table right here, this is looking at different types of molecules and the types of attractions that would be present. Couple thoughts within here. We'll start on this and we'll pick it up next time. When it comes to dispersion forces, notice they're saying those are always present. Whether it was an atom all by itself, a nonpolar molecule, a polar molecule, or a polar molecule with these particular groups on them, dispersion forces are always present. So that's one thing that we want to recognize. This one right here, you can have a more complex molecule, but only have dispersion forces present if it's nonpolar. BF3, CH4, those are nonpolar. If they're nonpolar, the only thing they have present are dispersion forces. If they start to be polar, then they start to have dipole-dipole interactions. So things like HCl, CH3CN, we need to be able to look at the formula there and determine whether it's a polar molecule or not. And then finally, we need to look at examples to consider if hydrogen bonding is present. This idea of classifying things based on their intermolecular forces and connecting them to other properties, let's pick that up next time. Let's stop here and we'll work on more ideas from chapter 11 next time. Really appreciated your attention. I thought you did an outstanding job.
Hey, Dr. Clark. So for both the B constant and the van der Waal constants, and determining like the intermolecular forces, does the size always refer to just the molecular weight?
No, it does not, but many times the molecular weight is going to be a pretty good indication of the size. It actually has to do more with the physical size, how large the electron cloud is, but usually the mass is going to be a pretty good description of that as well. I mean, clearly the mass is coming from things like the number of neutrons. That's not going to make a bit of difference, right? So if you were to say, oh, here's different isotopes, does that matter? It won't matter a bit, but that's a good way to have sort of a quick estimate how the mass, it's going to be a pretty good match for the size as well.
Okay, thank you. And I was also wondering, do you know if they're going to upload practice tests for the final, or is that not?
No, that's not usually, I don't know if we're going to have that as a resource at all. And the reason I say that is all of the stuff from the previous content, I think they all feel like, hey, we already have broadcast what those kind of questions are like. There's really nothing more to provide or practice that's not already, within Carmen. That's why I think that within my videos I posted on Perusal, I'm trying to narrow that down a little bit to help it so you don't have to revisit every idea in chapter 5, every idea in chapter 6. So I'm
Okay.
trying to narrow it down a little bit more from that. But usually they don't have the whole set of final exam practice stuff like they do for the other ones, because I think they figure, hey, we've already been telling people what our exams look like.
Mhm. All right. Thank you.
Mhm.